we have discussed quite a lot about searching, right? And how it relates to the basic concept of AI. What we have said so far is that when we are trying to find a solution to a problem, we try to conceptualize the problem first of all. And then after conceptualization, if it's a trivial problem, what we do is we make a mental picture, and then we think within the mind how to do it. We've looked at several examples, okay, and so we try and come to a solution within the mind without thinking too much about it. But when it comes to bit more serious problems, and when it comes to real applications, then we have to be more organized and systematic. And in general, AI, and that's one of that's the crux of the thing. In AI, we look at most of the problems trying to find a solution to the problem. Getting to that, when we say find, means go and look around. Go and look around. See if you can find a solution to the problem. Now, this going around doesn't mean physically looking out. It doesn't always mean that. It can mean a mental thinking. It can mean a piece of paper you sit down and discuss and decide, or you actually physically go and do it. But the crucial thing, crux, is that you try to find something. And when you're trying to find something, this means you have to make decisions that what should I do? Should I go straight or turn left? Maybe go backwards, turn right? So at each and every step, you are faced with the decision-making step. Should I keep going straight? You're trying to find your friend's location. You want to go to his house, his place. He knows where it is. He's sent you some information, and you're trying to find his house. So what do? You have it in mind. You have Google telling you take right or turn left. Sometimes takes you on a longer route, sometimes shorter route, and so forth. But the key thing is when you're trying to find a solution to a problem, you have to make decision on what to do next, how to get there. And that's what it is. So searching in the algorithm, that's a very fundamental concept. So problem solving, as I said, is just like agents. Agents, discussed elsewhere in another video, are what we're trying to replicate. So search techniques, mentioned already, and then we're going to discuss further, are universal problem solving methods, and rational agents or problem solving agents in AI mostly use these search strategies or algorithms to solve a specific problem and provide a solution. Problem solving agents in AI are goal-based agents. Goal-based, they're trying to find a solution, want to get to the solution, which is your goal. Basic terminology is just a repetition. As I said, you conceptualize, you create a mental picture, and then you try to put it down on, let's say, on a piece of paper before you start the computing side of it. Okay, so there's a search space which includes all possible situations that can occur when trying to find a solution. Okay, and you have a start position and you have goal position. The start is where you are now, and goal is where you want to be. Okay. In general, start is kind of given to you. Your goal also is given to you, but you could be a situation where you have multiple goals can be achieved through multiple paths, so to speak. Okay. But all of these possible positions, conditions, situations put together, okay, is called a search space, solution space, or problem space. We've discussed this in detail. The fundamental thing here is one, which is your goal tester. You start, end, and then something called a tester. We've already discussed this as well. Tester, what does it do? Given a situation, it works out, tries to find out whether it is the solution or not. And of course, the tester knows the solution. What does it look like? What is the solution? So it tries to match your given situation with the goal, and tries to reduce or tells you, no, this is too far, this is not the solution. So you move forward. Then the concept of search trees or graphs. What is a tree or a graph? Basically, It links one end, one node to another, and then another, and so forth. So graphs can be kind of linking between various nodes, and we call it trees as well, rather inverted trees. So a graph, you've come across several graphs, in your life every day. You look at the weather map with a graph, okay. You look at population statistics given in a graph and so forth. And then you convert that, or you try to look at it as a tree. So what's the fundamental difference between a graph and a tree? Graphs can have loops in them, okay. Whereas in trees, you look at physical trees that you're aware of. You've seen trees, but they don't, those branches, they don't loop back into the trunk of the tree. No, they don't. They keep on growing outwards. So that's the only difference, okay. But they are connecting. This is branch node, goes there, then goes forward, and so forth. And then the actions that you can take in the search space, and something called a transition model, which is that how do you move from one goal, one state to the next one. And fundamental thing, once again, one more time, the search space represents the complete set of all possible solutions. Tree representation of a search problem is called a search tree, rather inverted tree. So if you look at this figure that we've shown, you see a tree as it is, and then you look at the inverted tree, okay. So the only difference is, when we talk about representation, we are actually referring to the inverted tree, but I'm going to call it a tree, okay, that's all. So it has a base called the node, which is the base of the tree itself, and then instead of the branches going upwards, we will see the branching going downward, that's all. And the start node, initial state of the search tree, is the root node, as we call it, okay. Actions, and then what happens? Actions describe all the available actions available to the agent, okay. In the case of playing chess, each and every piece and its moves that are allowed. That's what actions and operators are. Transition model, a description of what each action does, and that can be represented in a transition model. Path cost, very interesting. Solution, optimal solution, you'll come across these. A path cost is a function which assigns a numeric cost to each path. Remember, now we're talking about traveling, searching for a solution, right? And each step that we take in trying to find that solution, okay, is actually adding to the cost. So you're a good chess player. I hope you've heard about the game. A good chess player would like to reach a solution that suits him or her as quickly as possible. There could be a solution depending upon the strength of the opponent, right? That it takes 100 moves to actually defeat your opponent, possible. What we are trying to find out is, or what I'm trying to find out is, how can we, instead of getting to 100 steps, how can I do it in 20 steps, for instance, right? So that's the path cost, how many steps, how many actions that I have to take to get to that solution. And of course, what is a solution? A solution, it basically is a sequence of action sequence steps. I take an action, I go there. What are the consequences? I take another action, see the consequences, goal or not. So a solution is a sequence of steps that lead from your start state to your goal state or goal node. Another interesting thing, optimal solution. What is an optimal solution? You're trying to find a route between one city and the other. You're trying to get there, right? Now there are, and you've heard about something called the traveling salesman problem. It has to, a traveling salesman is trying to visit, say, 10 cities, Lahore, Karachi, Islamabad, Peshawar, Faisalabad, Quetta, and so forth. Now for that traveling salesman, an optimal solution is one in which he doesn't have to travel too much distance, okay? It doesn't have to go from one city to the other 200 miles, 500 miles, 700 miles. There is some minimum there. But if you take another route, okay, then you might end up traveling more instead of, let's say, option 1 or option 2 or option 3. So these are solutions. Yes, you can visit each city, but an optimal solution will be the one that is the shortest possible if I can get there, if I can find it, if I can work it out. So as I said, traveling salesman problem. Climbing, say the Mount Everest. Okay, what is the best path? People actually climb the Mount Everest from the most dangerous side as well. Yes, people do it. People do it without oxygen support, right? But what is, if I were to do that, I would like to know what is the minimum distance that I need to travel. Now, however, it may be much more difficult. Like they say, you heard about the term called the crow flight distance. What is a crow flight distance between 2 points? Is that the crow flies from this point to this point in the air. It doesn't have to travel on the roads. It doesn't have to follow the signals, traffic signals and so forth. So that is considered as the shortest path. But anyway, so understand, in a situation where you have more than one possible solution, you look for the best possible solution, meaning just about the most minimum that I have to travel. Then there are a few properties of search algorithms. For instance, completeness. A search algorithm guarantees a solution. If it guarantees a solution, okay, it's called complete. There can be situations where the algorithm itself looks very good, but it can't find a solution. So it's not complete. So if at least one solution exists and that algorithm can help you find that, that's a completeness, sign of completeness. Optimality. Can you find the best solution? Based on, like, as I said, like distance or like time. I have to travel between cities, but I also want to make sure that my traveling time is also minimum and minimum distance and so forth. And so the lowest cost solution, if that you can find that, that's optimality. Interesting couple of other things. Time complexity. How long does it take for the algorithm to actually complete the task, find the solution? If it takes 10 hours, a very simple example, I'm sure you do, you keep on searching. Remember, Google started as a search engine. What is it trying to do? You're trying to find, you put a word there or a location or whatever else, and it searches for that. And as you can see, we are very much used to the fact that I put anything in Google, search for it, and comes back within seconds, less than seconds, right? That's time complexity. So how long does your algorithm take to bring you back the results? If it gives you best results, but takes, let's say, 5 minutes, you're not interested. You want to know there and then. You need to make a decision. You need to make a choice. So that best solution in all possible ways may not be acceptable. You'd say, just give me now. What's the best available now? Instead of I having to wait. Space complexity. Another very interesting one. How much storage, how much memory do you need to actually process this search? Okay. So search complexity basically is the maximum amount of storage or memory space that your algorithm will take in trying to get to a solution. So it depends on the complexity and, of course, of the problem. So all of these put together is actually helps us define, understand whether this is a good solution or that algorithm, or this is a good algorithm, or this is a good algorithm. You compare based on the thing that I mentioned. Now let's come to searches themselves. There are essentially two kinds. Something called uninformed search, and the other one is the informed search. The uninformed search, we also call it the blind search. Before I go into that, remember I've said this before, solution spaces can be represented as graphs. So now we are talking about graphs and trees, and each node represents the one of the possible solutions. Before I go into that, let me just also talk about some of the terminologies in the trees and graphs. If you look at this diagram given here, you see a few what we call as nodes A, B, C, D, E, F, G, H. This could represent anything, okay? And this is an inverted tree. We call it a tree, but remember it's an inverted tree going downwards. A, B, C, D, where A is called the root node, we identify that, okay? So that is the root node where we start from. And then B, C, D, everything else, they're called nodes in general, A being the root node. Then B is also called the child of A. C is called the child of A. Likewise, A is called the ancestor, okay, of the node downwards, for example, D. So A is the ancestor of D. D is the descendant of A. There are children and then children and so forth. And then in general, you call it descendants. And there's a common terminology we use in terms of families as well. So you have descendants, you have ancestors, which are your older generations, and so forth. Then within the same graph, the nodes D, E, F, G, I are called leaf node, leaf. So these are called leaf nodes. And the arrows, as you can see, are the edges or the links that connect the nodes. Look at another example. Now, how do we use graphs to represent important information with nodes and edges? As you can see in the graph, you have 3 boxes placed flat, and then you are trying to place them in a certain sequence, in a certain configuration, you're planning. So you have 2 particular options. You can see C placed on top of A, B separate, and then you have C on top of B, and so forth. So this is a representation, okay, of information with nodes and trees using, graphs. These could be, or you could be looking at city routes as well. And as I said before, graphs represent, are used to represent problem spaces and their solutions. Trees are more convenient in that sense that they don't have loops. So how do we convert graphs into trees? Okay. Remember, trees do not have loops. That's the only thing. Now let's look at one example. Okay. On the left are a number of cities with their connections shown. Okay. And the connection between them are the links, the distances, for instance. So on the left is a graph, on the right is a corresponding tree. So what you do is you start with, let's say, the first one, which is your S start, call it. It's connected to 2 different cities. So you make that as your reference node, and then show the graphs where it is linked. So it is linked with, let's say, cities A and D. That's your root node, and then you keep on combining. As you can see, the loops are removed, but the nodes themselves are being kind of replicated. Okay. Right. Now let's look at a city map, which is just about what we've shown to you. A graph shows, the example here again, a city map of cities A, B, C, D, E, F, and G, and their links. We make S root node and so forth, and we come to the tree representation of that. Now, having discussed all of this, come back to when I mentioned 2 basic categories: blind, uninformed or informed searches, as well as a couple of others that I initially spoke about. Okay, and when we will explain these, we'll try to use the same mouse maze search problem that we started probably initially from day one as well. A mouse looking to find a cheese in a maze. So start with a blind search, okay, uninformed search. The mouse is in general looking for food. It doesn't know if food exists, and it goes into a maze, and what it does is tries all possible combinations, turn right, turn left, looking for food to eat. So it's following something blindly. It's looking for food. And it will keep on searching, looking for food in all possible directions without realizing, without somebody telling the mouse, guiding the mouse that, don't turn right, it'll take you away from wherever you're looking for food. So this is a blind search, uninformed search. So it's a purely hit and trial method. Generate and test, remember we discussed. So hit and trial or generate and test. Try all combinations, one of which will actually succeed. Okay, now moving on, let's say that the mouse is not only hungry, but the cheese itself is fresh and it's got some smell, okay, of the cheese. Now in this case, if the mouse can sense, feel the smell of the cheese, that is a driving force, that is a guiding force, and the mouse intuitively will actually go in that direction. That's what happens. All of these animals, insects flying, they're guided by their sight, line of sight, and two, by their sense of smell. And of course, some animals have sense of hearing as well. In this case, it's a smell that guides. So that guide, the smell in this case, is what we call a heuristic, a guide, heuristic, a rule of thumb that we discuss later on as well. Okay, so it actually tells the mouse, don't turn left, go straight, and the cheese, the smell gets stronger and stronger. That's what it is. So stronger the smell, right, correct is your direction. So this is also called informed search. You have some information on how to get to your goal. Now, remember this is a guide, but it may not always work. This heuristic word I use, rule of thumb, is not always guaranteed to succeed, but most of the time it will. We'll find out as we move on. In here, you can see various routes that the mouse tries until it comes to the solution. In here also, you can say any path solution. So the mouse is only interested in getting to the cheese, and the faster it gets there, the better it is. It won't look for any other options. So if you have a path and you have two possible choices, okay, in case of any path search, we are only interested in finding any one solution to the problem. And if we find a solution, we don't worry about the solution and we say, stop, we've done what we wanted. And this is what the mouse is doing. It's not going back, it's not looking for optimal, it just wants to get there without considering any other solution. So the question is, for instance, is there life on Mars? That's a question. If you can answer that question, that's it. You know there's life on Mars. Then comes the next question, how to get there and so forth. So that's any path solution, I would say. In mathematics, trying to prove a theorem, okay, can you prove a theorem? That's your question, okay. And if you say yes, I can find a solution, your job is done for the moment. How to get there is a secondary thing. Trying to discover new compounds, okay. If you can discover a new compound, forget how you got there, but you did. Next comes the optimal search, okay, the best solution that I discussed elsewhere as well. You have a number of options. From amongst all of those possible options, what is your best option, okay, which is least cost, let's say, minimum time, minimum complexity, and so forth. So as you can see in the diagram, maze search, blue is probably the optimal path. It is shorter and requires lesser number of steps. So in optimal searches, we look for least cost solution, already said that. Once again, a traveling salesman is a very typical example. Talking about, once again, informed and uninformed, blind searches, uninformed searches have no specific problem related information available to them. We call it as domain knowledge that's specific to that particular. For instance, you're trying to determine the patient, what problem does he have? Okay. If you are a medical expert and you have some domain related medical knowledge, yes, you will not waste time in unnecessary trials and errors. You want to come to the solution there and then. In the case of the maze problem, closeness, location of the goal, okay, that maybe is a good domain specific information related to the problem. And of course, the blind searches are also called brute force method. You put in all your energies and you say, yes, try out all possible. I have enough time, enough force, let's do it. So you try out each and every node and every leaf in that tree until you get to the goal. Coming to the heuristic part I mentioned earlier, when you have domain specific information available to you as a guide, then your search becomes much more efficient than, let's say, uninformed. A heuristic, it's an English word, a heuristic is a rule of thumb. It's a rule of thumb that helps the person solving the problem cut down unnecessary search, as in the case of blind search, brute force. It doesn't go on unnecessary paths. For instance, if you go to a doctor, a patient goes to a doctor with, let's say, pale eyes, and the color of the skin is also pale, most of the time, that's what the heuristic is. Most of the time, the doctor will identify you as patient suffering from, let's say, jaundice or some kind of a hepatitis problem. That would be true 80-90% of the time. Okay. The other 10 or 20%, it could be something else as well. But most of the time, and that's the heuristic. So a heuristic will actually help you cut down unnecessary search, but let's say 80% of the time. So it is not guaranteed to succeed, but an intelligent person will actually make those decisions, and most of the time come out correct. This happens in chess as well. You find a solution in reasonable amount of time. That's what the doctor is all about. You go to an emergency situation. It has only minutes to decide, otherwise the patient is expiring. It has to take intelligent, rules of thumb, heuristic information, and experience put together to actually find the most probable cause of that problem, but not always guaranteed to succeed.